Hello, everybody. Okay, so we're back and we're going to be talking about image and kernel. Okay, let's flip to the right page. So this is 3.1. 3.1 is part of a chapter called Subspaces of R and Their Dimensions. Okay. So the basic idea of the image of a function. So right now we're going to sort of call image and kernel kind of like range and domain. There are some differences, and that's something that I'm going to have to talk about with Dr. Prudham when I get back from spring break and we talk about it. So I wouldn't fall back on that definition, but if you kind of get confused with these terms, I think it's good to sort of ground yourself in that a little bit. But of course, don't take that as gospel. That might change once I talk to Dr. Prudham. But we're going to start with the idea of the image. So it consists of all, oh Lord, that was too much. Okay. All values that a function takes in its target space. There's sort of another way of writing this, which is that image, and we just sort of shorten image to im of f is all of the f of x's for every x in x. If we say that B is in Y and B equals f of x, or then B equals f of x for some x in x. So in other words, the image of f is basically all of the f of x's that can happen for that can be the output for any of the x's in the function that we're dealing with, right? A good way to think about it is with this drawing, and this is where I'm saying that it gets a little complicated with range versus target space versus image, because I've also, kind of looked it up and heard people say that the target space is really the range, and the image is a little more specific. But that is sort of what I've got to talk about. But we're gonna go with this drawing right now for a little bit of clarification. So this is X. This is the domain. This whole thing here is Y, the target space, or what I'm going to call the TS. And this is the image. So it's kind of a good way to sort of think about it a little bit. But we've got an example that's going to kind of show this, or kind of put this in another way. One thing that I've noticed about this sort of first lesson is that it's been a lot of time explaining image and kernel in just different words. I think it's sort of that logic that, like, when you're first learning a math concept, sometimes some things will land with some people and some things won't. I know this from personal experience. Like, I remember very specifically in third grade when everyone learned decimals, it took like the fifth explanation to actually, hello? Sorry, guys, thought someone was at the door. But anywho, it took like the fifth explanation for me to really understand what that was. So, just some words work for some people, other words work for other people. But here's another way of thinking about image. So we're going to take this function, and right now we're just dealing in functions. We're just dealing with functions. Okay. So the image of, we've got this exponential function f of x equals e to the x. Should be, pretty, just kind of a flashback to pre-cal and algebra 2 and everything from R to R. And it consists, so the image consists of all positive real numbers, right? And the way that we can think about this is we can write every positive number b can be written as f of ln of b, right? Like every x can be written as ln of b. And for some b, right? That's not important. That's just like moving e's around and turning them into ln's. But given this, the fact that's important for thinking about kernel is that they explain that we can use this example to kind of say that the image of a function, so the image of a function f of x consists of all real numbers b such that the line y equals b intersects with the graph of f, right? So basically the image is for every point where this line, this dotted line right here, intersects with this line, right? And I mean, as we can see, it's going to be for all positive real numbers because every point on this line is going to intersect, or because every kind of positive b, y equals b line here is going to intersect with this function. But I thought that was a really helpful way to go about thinking about it. But then the third example that we're going to take here, we're going to introduce an idea called parametrization. Okay, so parametrization is a really fancy, really long term, but it's actually pretty simple. So we're going to be looking at the image of the function f of t is the vector of cosine t and sine t. Okay. From R to R2. Okay, so we've got cosine t and sine t. So what they point out is that the image of this function is really going to be the unit circle. And I can draw this and explain why. So if we've got some, and I'll use a different color here. We've got f of t for some cosine t sine t. And here's t right here. Well, the sort of output, the possible outputs are going to be anything along this line, right? Because if we think about, t will change, right? So t could be here, 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 right? And it will correspond with something along this line, right? And any t, you can come up with any point along this line by plugging just in a t, right? So our image is going to be the unit circle. And we can then say that cosine t sine t is actually a unit vector for all t. Why is this true? Well, this kind of goes back to things that you would have learned in pre-calculus, having to do with trigonometry. But it's sort of just like a fact that cosine squared t plus sine squared t equals 1. So if that's true, then that means that cosine t sine t is going to be a unit vector, right? Well, if that's true, then that means that any unit vector u in R2 can also be written as cosine t sine t. So that's kind of just like an added fact. But the important thing is that this function is called a parametrization of the unit circle. And sort of a general definition of parametrization. So a parametrization of curve C in R2 is a function, F stands for function, from R to R2, whose image is C. Right. So in this case, the curve C is the unit circle and the function is cosine t sine t, and its image is that curve. But as we'll see, once we get into the problem set for this chapter, this can apply to spheres, it can apply to ellipses, it's anything with a curve, where the image of a certain function is that curve. But this is an example of where the image of a certain function is the unit circle curve. Okay. Let's see. Originally, I was going to stop our video here. And I think I still am. Yes, I think I'm still going to do that. But I will come back with more stuff to do with this.